While we will not cover all of Chapter 0 in this class, I do want to make you aware of the fact that the information is there for you as a resource if you need a refresher on any of the mathematical operations we use in chemistry. In this lesson, we'll briefly review Section 0.02 on exponents in scientific notation. The textbook authors have two goals: use exponents successfully and be able to convert between standard and scientific notation. An additional learning goal is for you to use this ability to convert between scientific and standard notation routinely when solving problems. This should allow for lots of practice. Let's begin. An exponent tells us a number is being multiplied by itself. For example, 5 cubed means that we are multiplying 5 by itself 3 times to get 125. Here, the number 5 is the base, and the number 3 is the exponent. If we encounter a negative exponent, it means we also must take the reciprocal of the result. So 5 to the negative 3 would give us 1 over 5 cubed, or 1 over 125, which is the same as 0.008. A tricky fact to remember is that any base raised to the exponent 0 has a value of 1. In chemistry, we often encounter numbers that are very large or extremely small. We can use metric prefixes or powers of 10 to express these numbers more easily. Going the powers of 10 route is called scientific notation, which has its own set of rules. The first rule is that the coefficient, the number to the left of the decimal point, can only be a number 1 through 9. If it's less than 1 or greater than 9, you must adjust the exponential part to get it between 1 and 9. In the exponential part, scientific notation always uses a base 10. A positive exponent on 10 tells us we're dealing with a big number, while a negative exponent tells us we're dealing with a small number. For example, 1.73 times 10 to the third would be written as 1.73 times 10 to the third equals 1,730 in standard notation. As you get more practice, you'll see the exponent is simply telling us how many times to move the decimal point. Take some time to review this chart to become familiar with how many times you've moved the decimal point from behind the 1 here to get a number such as 10 to the negative third or 10 to the third. Let's try a practical example. We'll be using Avogadro's number a lot in chemistry. Rather than writing it out like this with 20 zeros, it's much easier to write 6.022 times 10 to the 23rd. Note that I had to move the decimal place 23 places to the left to get the coefficient to be between 1 and 9. The exponent becomes 23. For a small number, we want to make it look bigger, so we move the decimal to the right in this case, 14 places. The exponent becomes negative, indicating this is a small number. It may sound silly, but the way I remembered these differences between positive and negative exponents in scientific notation is this. If my size is really small, but I put on something that makes me look bigger, that's a negative result. Here are a few examples for you to try. How do we express 1,450 milliliters in scientific notation? How do we express this small number of grams in scientific notation? How do we express 29,029 in scientific notation? That is it for this particular lecture, and there are no author's notes to share, so just find lots of practice problems in the textbook and let me know if you run into any problems.